After studying the direction of EMF by Lenz's law and magnitude of EMF by Faraday's law, now let's consider a new type of EMF, which is motional EMF. First of all, let us see this motional EMF is this type of EMF or another type. But here it is clear that it is the induced type of EMF. So the first characteristic, the magnetic flux which is linked with the coil can be varied by many ways, and from that, after changing the magnetic flux we can have the value of EMF. So first of all, let's consider the different ways for changing the magnetic flux. So the first way to change or vary the magnetic flux is the magnet can be moved with respect to the coil. So the direction of magnet and the direction of coil should be opposite to each other, or either one is steady and the other one is facing the object. So here the object we are taken as coil. So suppose here is the coil and this is the suppose a bar magnet, north pole, south pole, and with this the north pole should face the coil. Now the second one is the coil can be rotated, and in this case what happens, as the magnet comes nearer to the coil there is a increase in magnetic flux, and when this coil will move farther from the coil the magnetic flux will decrease. Here the coil can be rotated in the magnetic field. So what happens in this case? Here we are only changing the angle between the surface area and the magnetic field. So we are not actually rotating the coil, but we are changing the angle between area and magnetic field. Now the third one, the coil can be placed inside the magnetic field. In a specific position. So here the position is specified of the magnetic induction. and the magnitude can be changed with time. Now comes the fourth one, which is very important. The magnet can be moved inside a non-uniform magnetic field. See, we have considered one case of non-uniform magnetic field, and here we are placing the magnet. The fifth type is by changing the shape of a coil. So in this case, to find out the magnetic flux, there are different values according to their area element, and you have to change the shape of a coil in magnetic field, not outside the magnetic field. So according to this, now I can write down the definition of motional EMF, that the induced EMF produced in a coil due to the change in the magnetic flux linked with a coil due to some kind of motion is called motional EMF. So this is the kind of EMF which has been produced due to the change in magnetic flux. So if there is no change in the magnetic flux, then there will be no motional EMF. So this is one characteristic about it. Now, to obtain such kind of EMF, you just consider the following situation or arrangement, which I am going to provide a figure. So this is the figure in which we can produce the motional EMF. So which are the content which are used over here? First of all, this is the U-shaped conducting wire. Then this is placed in non-uniform magnetic field, or sorry, uniform magnetic field. This is the uniform type. Also, this uniform magnetic field is directed normally into the plane of paper in such a way that the plane formed by the conductor remains perpendicular to the magnetic field. So see, all these planes PQ and P dash Q dash are parallel to the magnetic field. Also, if you see that the conducting rod PQ this is all type of arrangement you can write in your language. It is not necessary that you should write each and every word of book. You can write in your explanation. Now, this rod is moved with a constant velocity v. So, here v is constant velocity of the two arms of U-shaped conductor. Here we are assuming that there is no energy loss due to friction because here the U-shaped conducting wire which is containing of surface and with some kind of friction, but here we are assuming that there is no loss of energy due to friction. Now, the velocity of the rod is moving with maintained constant velocity and by applying the force having some magnitude. So I am supposing here that the normal distance between two arms of U-shaped conductor means which are the two arms C, R and S. So that is equals to L. Here the value of RS is equals to L and the RQ and SP both are having the value X. So with the use of these quantities, now I am trying to find out the magnetic flux of the loop PQRS. The magnetic flux of loop PQRS is phi is equals to BA and therefore what is the magnetic field? This B is magnetic field or we can say as it is the magnitude. So I am writing over here magnetic induction into the multiplication with area of PQRS. Therefore, phi is equals to the magnetic induction will be as it is. Area of PQRS means length into breadth. So length is L and breadth is X. So it is the new equation for find out the magnetic flux. Because whenever you have the value of magnetic induction, the value of length and the value of breadth, so you can easily find out the value of magnetic flux. Similarly, according to Faraday's law, CF will be capital no matter whether it is in the middle of statement. So, epsilon is equals to minus d phi by dt is equals to minus d by dt dlx. Now see, The magnetic induction will also not change with time. Here, the length means U-shaped conductor will also not change with time. So these two quantity are constant with respect to time and hence I can put outside the differentiation. But this X can be changed with time because the force is continuously acting on the system, or we can say the U-shaped conducting wire, and so there is a displacement of rod is possible and therefore the induced EMF will be minus dl dx over dt. Now see, here x is the displacement because it is the RQ or SP, both are having the same value. So this is the displacement of the rod from the original position, means the arms of the PQ. It changes to RQ and hence this X is the displacement. So the rate of change of displacement with respect to time is nothing but velocity. So the equation will modified to minus dlv, where v is the velocity of the rod. Now here the motion of the rod is responsible for generation of induced EMF, because here v is the velocity of the rod and generation of induced EMF, and hence this EMF is called motional EMF. Thus we are able to produce induced EMF by moving the conductor instead of wearing the magnetic field. So this is the another kind to produce the magnetic field, or we can say the induced EMF. Now suppose if the rod is moving in a magnetic field without the U-shaped conductor, then also such kind of EMF will produce with the help of that origin. So what is the origin of generating the induced EMF? So that we will see in the sub-article of 1.6. So let's start the new topic, the origin of generation of induced EMF. So as we discussed in the previous article, to find out the induced EMF, in which we have used the U-shaped conducting wire, but it is not necessary to use the U-shaped conducting wire for generation of induced EMF. So this statement suggested that there is another technique from which we can find out the value of induced EMF. For that I am giving you a structural arrangement. So in the figure, a conducting rod PQ. So see, this is not U-shape, but we have used a conducting rod. PQ moves in a magnetic field. So here I am considering the magnetic field as V. Also, The plane is perpendicular, which is clearly shown now. The positive ions and electron in the rod will also move along with it because there is a positive and negative ion. Here electron is shown which has a negative sign in the direction of the motion of the rod. So suppose the motion of the rod is supposed downward, means this direction. So the motion of the particle is also downward. Now you have to consider one more thing, that in the present case the velocity is perpendicular to magnetic field. See, the direction of velocity and the direction of magnetic field. So both are perpendicular to each other. So this is very important case. Hence, they are experiencing the Lorentz force. They mean the particle actually. And this Lorentz force is given by F vector is equals to Q into V cross B. So here Q is the charge of the particle, V is the velocity of the particle and B is the magnetic induction. Here you can find out the direction of force by right hand screw rule. And this will be normal to the direction of V and direction of B. Here, the positive ions will experience the force from point Q to point P. Let me give you the figure again. So the direction of force is along this side. So this is the direction of force. Here I am writing F, and it is the direction of motion. So I am writing over M. As they remain fixed at their lattice point. So these are the nothing but lattice points, means fixed points. Now, whenever the force existing from point Q to point P, the end Q of the rod becomes negative. So here Q will become negative and Vp will become positive, and hence the rod behaves as a battery. With EMF, epsilon is equals to BLV. And with this, our subtopic of article number 1.6 is over. There is another subtopic which we will discuss in the next class.